Okay. How's everyone doing? Bad. Someone did point out that I fucked up and I should have like had a observing night last night. And so I have some like witty rebuttals, but I'll just admit that I fucked up. So that would have been a great opportunity to go look at Jupiter. And in fact, tonight is still a really good opportunity to look at Jupiter because Jupiter is moving relatively slowly. It's not like we're like moving away at light speed. So even though it's really bright tonight and you can go out there with a good pair of binoculars, if you don't own a good pair of binoculars, that's perfectly okay. You should still be able to see the bands. And if you have really, really good eye, really, really dark skies, you can see the moons. But of course, none of this matters because that's all to like try to trick you into liking astronomy. You already love astronomy, right? So we're about to get to the Jovian planets. And let me tell you, what's better than looking at something with binoculars? Sending a spacecraft with an iPhone, right? Because we all know iPhones take pretty good pictures. You strap this thing and then you get really close. And I'll tell you, the quality of those photos is ridiculous, okay? So get used to like a little bright dot in the sky. And then when you see Jupiter, you're like, I get why he wasn't excited. I also fucked up because on Thursday, it was actually a really cool day. Does anyone know what Thursday was? It's called the fall equinox. Okay. So equinox means that you would basically have equal equinox, half day, half night. So currently we are in the time of the year when you are starting to have more night than day. And that will continue until, sorry, say that again? Winter equinox. Spring equinox. So there's a winter solstice, and that will be when the days are, the nights are the longest. Okay, and then it'll go back towards spring equinox, they'll be equal again. And then you have summer solstice, and everyone's playing, having a good time. And this is only valid for the northern hemisphere, but I assume most of us spend our time in the northern hemisphere. Is that wrong? Okay. So today we're going to talk about light. Anyone know what this is? Spectrum. Another word for this is the easy one. Rainbow. This is a rainbow. You've seen these, hopefully. Has anyone not seen a rainbow? Okay. So these are all of the lights. This is all of the light that the sun is giving you that our eyes can see. If you're a man, you are more likely to not be able to see, say, this section. You might not think there's any color there. You might be red, green, colorblind, for example. You can go online and make these really fun, they're not games, but you can like sort the order of the colors and see where you're deficient in your color vision. I've done all of them. I'm color deficient in blue-green, but that's okay. And we're going to talk about everything that you see here. This is indeed the sun. We're going to talk about the different types of features we see here. The motivation for this is that we are stuck here on Earth for the most part. We've been stuck here for a while. And most of the information that we get from the world around us is through the form of light. In fact, I get most of my information about the world through light. For example, I know that this table's here before I walk into it. So this would be touch, this would be vision, right? So we want to understand this concept of what light is. And then we want to make sure that we understand what types of light are hurtful, helpful, etc., and how they interact with one another. You might be saying to yourself, this is a weird time to start learning about light. Well, it turns out that if you want to understand how an atmosphere works, it depends entirely upon your ability to understand light. Any questions before we start? What's that? Not just whether the sky is blue or a different color, but every component of the atmosphere is driven by light from the sun. Kind of weird to think about. You think about your day-to-day as being like, not so tied to the sun, but in fact, that's what's driving the place. Okay. So what are some different kinds of light? X-rays. Good. What do we use those in? Looking at bones. Good. They look right through your skin. Also used maybe in airports, right? Okay, that's a form of light. Good. Infrared. What's that used for? Heat. Yeah, it's produced from things that are hot. So snakes use it to see. Sick. So they're in like a cave. They can like see a bat flapping around. It's giving off infrared light. Pretty cool. Yeah. Ultraviolet. That's a fun one. What does that do? Gives you cancer and also makes you tan. So you spend time at the beach, you turn a different color. It's because you're burning on the outside. And that's from the short amount of light that comes in the ultraviolet from the sun. The sun makes a lot more ultraviolet, but thankfully we don't access that. So if you're out in space, you take off your spacesuit for some reason, and you want to tan, you will just like burn right away. Tons of UV. Okay, so we got a couple. We got UV, we got infrared, we got X-ray. Yeah. Gamma rays. Okay, we all know the Hulk was created with gamma rays. Very scientific, right?
How about white light?
White light. Yeah. What about the light that we're using right now? So it's called visible. Let's throw that in there. Is that it? Anything else? How does this work? We know what that is. That's creating light. That's the red thing that you see on the screen. That's light. But how does it tell the computer? Go forward and backwards and sometimes through the arm. How does your phone work? How does this just magically connect? Hello? What does it do? The wire that I can't see? Yeah. Radio waves. That's exactly correct. Okay. Radio waves can carry information. Form of light. Weird. Anything else? You don't have to memorize every type of light. We got most of the ones that are important. There's one that you probably use. There you go. Microwaves. So microwaves are cool. Microwaves do not give you cancer, regardless of what your mom told you growing up. Okay, you stand really close to it, you're not going to die. But if you stand too long outside, you may die from seeing it. Okay. See if we got them all. We got visible, we got X-ray, we got ultraviolet, we got infrared, we got microwave, we got radio. Okay. So we talked a little bit about white light. We saw that if you put it through a prism, so maybe you've seen this in like high school, or I don't know when you first see a prism, elementary school, you play with a prism. And essentially what you see is you have some lamp here, and you add a little slit. This is just a panel that blocks to collimate the light, makes it a nice little light column, and then you put it through this piece of glass, and it bends the glass into a rainbow. And this is exactly what's happening in a rainbow, except for the thing doing the bending, these water droplets. So spherical water droplets happen to bend light, and they bend it according to the properties of the light itself. So you'll see one of these, the main one, and then sometimes you'll see a double rainbow. Looks familiar with that? You like look in the direction of the rainbow. There's one outside of it. Okay. There's also a double here, but it's really dim and it's off to the side. There can be many, many of these. You can see sometimes triple rainbows, quadruple rainbows. They're just dimmer each time, so they're really hard to see. Okay. So we are talking about this little tiny piece of light. And what we should be talking about is what's called the electromagnetic spectrum. And it relates the types of light we've been talking about: gamma rays, the X-rays, the ultraviolet, visible, infrared, microwave, and radiant. And the property that's changing as you move through them is how close the wavefronts are. So the way that I like to think about this, light is sort of weird. In fact, it's very weird. It behaves both like a wave and like a particle. What do I mean by that? So let's say there's light coming from here. It's going to bounce off, say, your computer. It's going to bounce into my eye, and I'm going to be able to see. If I place my hand in front of the computer, I cannot see it because all the light gets blocked by my hand and none gets through. Just like you would imagine if someone was throwing, say, tennis balls to a wall, nothing gets through the tennis ball. But waves do something different. You put, say, a wave front, it's moving, you place a rock in front of it, it'll just bend around the wave. You get some of that wave behind it. That make sense? Light can do both. So light can act like a particle or a wave. When we see things, it tends to be acting like a particle, but the properties that it have are wave-like properties. So just like you're listening to me right now, what's happening is my mouth is emanating sounds. It's pressing air, and that pressure is going to touch little hairs inside your ear, and the vibration of those hairs are going to tell your brain that I'm speaking. Now that's amazing, but I don't know exactly how that works in my biology. But that same principle is true here for electromagnetic spectrum. So we're going to use this analogy. It's really important. So when I say something like blue light has a different frequency than red light, you can think of that as pitch. You can think of that like tone, right? So for example, if you have a high-pitched noise, you have multiple wavefronts hitting you very quickly. It's going to sound really green. Whereas a low-pitched noise, for example, it's going to sound like bass. Hear the difference? I know I'm not a good singer. Okay, so blue, high pitch, low pitch. Okay, so this is the part that we can hear. It's the part that we can see. Just like dogs get really annoyed anytime you put on the vacuum cleaner because they are hearing sounds that we don't have access to. You can also take another test when you go home. You're going to take 2 types of tests today. You're going to find how old your ears are. You can go online and say, can you hear this noise? Say yes or no. Go a different one. Can you hear this noise? No. As you get older, the hairs in your ears start dying, and you stop being able to access higher and higher pitched sounds. Okay? You get really old, you just lose all your hair. So we can only access this tiny bit of light, but of course, we have wonderful computers and cameras. And for example, this thing right here can take in all of these different types of light, and it can even put some out. Okay? So for example, in this part, it takes in visible, but it also uses some of the infrared in order to take like dark photos. You ever seen that? They like hold it still, and then it waits and it like accumulates light. It's using infrared light to make that photo. And over here in the radio, it's getting the information about the text message from my mom. You can't see the receiver. It's very big, radio waves are big, but the whole thing is built into this little box. Okay. Okay, I'm gonna walk through this in more detail, I promise. Let's talk about the different sizes of these waves, the real waves, okay? So here is a wavelength. This is the distance between adjacent peaks. And this is why, if you look in the visible, it's the average size, say, of a bacterium. Usually, if you were dealing with something that has a lot of waves, say very frequent changes, it's going to be sensitive to the actual object. So what do I mean by that? I mean that if you imagine some giant wave, say a tide on Earth. You're standing there, and you're waiting for 6 hours. And you watch the wave go from the bottom part up to the top part, and then back down again. Okay? That's going to look very slow, going to be very boring, not very interesting. The one that's more interesting to you is standing at the beach, and they're coming in and out every minute or so. When you're a little kid, you're really excited, right? So that frequency, how often they're happening, is changing, right? In these different types of waves. Here, you have really long waves, football field length waves. So unless you are also the size of a football field, you're really not going to notice it. Our eyes, not football field size. They are about animal cell size. And they're very good at reacting to animal cell size light. Okay? Our eyesight here in the visible corresponds really well to the bacterial side. Something like a baseball or a pinhead. These are sort of more microwave size. This is why your microwave box is probably about this big in general. Can't really make it much smaller, because that's like the size of a wavelength. A couple wavelengths in there. You go onto the other side, it's even shorter. These shorter ones, you'll notice here's a hydrogen atom. It's like the smallest atom that we know of, and they get even smaller than the smallest atoms. You might be thinking to yourself, well, that's kind of breaking, but I understand. I don't really interpret that. Well, that's good, because these are the most powerful rays in the universe. And in fact, when light is coming at you in gamma ray form, it's probably going to destroy what you have. Okay. There's frequencies, don't memorize them, they're basically meaningless. Just how often am I getting a wave front in every second? So 10 to the 20 wave fronts in a second, that's a lot. But to go back to our analogy of high pitch and low pitch, you can see that here. So higher pitch, lower pitch. Higher frequency, lower frequency. The red light, for example, has a lower frequency than blue light. Okay. Okay, so this is related to energy. On the left-hand side, you have high energy. On the right-hand side, you have low energy. And thankfully enough, they're directly proportional. I don't have to do anything weird about it. If I know what these numbers are, I can just convert between them. And so, for example, if you've ever wondered whether having your phone next to your ear or having the Bluetooth is better for your brain, well, in fact, they're the same. Because the Bluetooth that's in here and the waves that are coming out of this phone are the same waves. Exactly the same waves. So whether or not they're on your ear or next to your body, they're the same energy, same wave. Okay. They're also not dangerous. It's called non-ionizing radiation. Up here, you'll see that the radiation, the type of light that can impact a protein, is over here in the ultraviolet. Bacterium, sure, you can clean stuff with bright lights, disinfecting lights. Over here, animal cells affected by infrared light. In general, what you're doing with a microwave is you're warming up the water molecule. Water molecules have a natural vibration, so they like move like this. And if you can warm up the water, you can warm up your food. That's why if you put metal into a microwave, it gets really upset. Why does it do that? Because there's very, very little water in metal, and it's trapped. And so suddenly it starts to move, and it can't get rid of any of its energy. So it heats up the metal, and the metal gets on fire. Okay? So don't stick a metal in the microwave. Okay. So there's your energy ladder. Down here, very low energy microwaves, very safe. Radio waves over here. Let's say you live next to an energy line. You're really worried about, oh my God, it's making noise all night. Okay. All of this stuff right here, low energy. Now, you live next to a nuclear reactor, or you live next to someone who's doing x-rays, like a dentist. So you're a dental assistant. You're standing next to the x-ray machine all day. Probably a bad idea. Probably a bad idea. Okay. Here's your natural sources in the world. This is where you're going to find them all. Radioactive elements going to give you gamma rays. If you're running into these often, let me know. It's a bad thing. Okay. X-ray machines, we just talked about that. We know about where light bulbs come from. Yes. Sorry, we know where visible light comes from. This. People, as we mentioned, emit in the infrared. So, for example, if you're playing one of these video games like Night Rain Vision, what is that actually? That's seeing people with infrared light. And they make infrared cameras, fully infrared cameras, which are pretty cool. You can like check someone's temperature. Treat them with a gun. It's like, oh, you're have a fever, you probably have COVID going, right? That's using infrared light. You have radar here. Now this is kind of in the wrong order because radar spans this whole thing. It's a little annoying, but microwaves are just a subsection of all of this. We're not going to spend too much time on that. Okay. And there's also cosmological versions of all of these. So for example, the most energetic sources in the universe are called gamma ray bursts. Just like a really bright object of gamma rays. Why are you doing that? And there's these black hole accretion disks. We won't talk about them, but if you take the 1010 series, we'll talk about what black holes are in more detail. Very energetic objects, and they create X-rays. Then the sun's chromosphere is where we get all of our ultraviolet light. It's what causes people to tan in the first place. Cancer. It's coming from the very top of the sun's atmosphere. The sun itself, the very surface, gives us the visible light. Okay, so when you look up in the sky, you see a sphere. You're probably seeing the sun's surface and not the chromosphere. Then you have planets, star-forming clouds, just like us. They're hot. They're going to give off infrared light. Cosmic microwave background. This is the edge of the observable universe. And radio galaxies. They emit in the radio because of how hydrogen works, but you don't have to carry that out. Okay, so let's go back over the light stuff. Questions? I know this is all really weird and stupid, right? Okay, good. Weird and stupid. So here's light as a wave. Here's how to think about it. Here's a wave. Okay. Let's talk about all the properties. There we go. So wavelength is the distance between two adjacent peaks. It can also be the distance between two adjacent troughs. It's just not from a trough to a peak. Okay? And because they stretch so far, they use many different types of lengths, meters, nanometers, angstroms, etc. Typically, it's represented with this letter lambda. And this can be from kilometers, as we saw before. Radio waves are kilometers large, it's smaller than a hydrogen atom. Okay, frequency is represented with F, and it's the number of times per second that a wave goes up and down. So if you're standing at the seashore and you see waves go by you, for example, let's say you're standing in the water, watching waves move by you, you count them, how many go by you per second? Okay. So the higher the frequency, the more peaks and troughs go by you. Does that make sense? Okay. All light travels with a constant speed. This was not known ahead of time. This had to be discovered. Kind of weird. When I speak with something called the speed of sound, propagating in a medium, about 300 meters per second. So it happens pretty close to instantaneously. But if you're really far away, you'll notice that it takes some time. If you saw lightning, for example, you see the light, and then maybe 10 or 15 seconds later, you hear the boom. That's because they're traveling at different speeds. Light travels very quickly. Sound doesn't necessarily travel very quickly. If you look here, speed of light is 300,000 kilometers per second. Doesn't mean anything. I don't know what that means. But over here, this number is much more meaningful. 670 million miles an hour. Okay? So the amount of time it takes to get from, say, you to my eyes, it's almost instantaneous. I'm seeing you basically as you are seeing yourself, very little delay in between the two. Now that's not the case for the sun. Remember when we originally talked about how far away the sun is, we said it's about 8 light minutes away. So even traveling at 671 million miles per hour, it takes 8 minutes for the light to get to us from the surface of the sun. So if you're like a little light piece, top of the sun, you just get born, takes you 8 minutes to get here, traveling super fast. Okay. Questions about this? Okay. So how are wavelength and frequency of light related? A, if wavelength increases, so does frequency. Direct relationship. If wavelength increases, frequency decreases. Inverse relationship. C, it depends on the speed of the light wave. D, it depends on what type of light we're using. Or E, they're not related. Are you ready for your quiz? Three, 2, 1. Okay, interesting. Okay, I don't think any two people sitting next to each other had the same answer. So go ahead and turn to the person next to you and see if you can convince them of your answer. If you're with a group of 3. Okay, ready to revote? Great success. Okay, let's vote on 3, 2, 1. Oh, interesting. Okay, we've got most people to agree on one of 2 different answers, either A or B. You don't want to defend their answer? Yeah.
Actually, you propose the spectrum. The more the wavelength increases in the length, you get a shorter frequency line. It just switches. Wavelength decreases with the entire time of wavelength.
Right. Right. So if we look at that, let's put that into the right. Okay. So there's that picture again. And just like you're saying here, so this is the distance between peaks. If you have more of them pushed together, then the distance between them is smaller. Okay. So for example, we can write these in 3 different ways. We can say that the product of the wavelength and the frequency will always be equal to a constant. And that constant is the speed of light. So another way of saying that, if I want to get wavelength by itself, it's down here, is the speed of light divided by the frequency. So they are inversely related. If this is big, then this is the same size because it's a constant, and this has to get small. Similarly, if this is big, the wavelength, this is not changing in size, and this has to get smaller. Questions? Okay. Shorter the wavelength, higher the frequency. Cool. Interestingly enough, light has energy that's proportional to frequency. So I hinted at this already. This is how we write it. This symbol that looks like someone cut off the edge of an infinity sign, called proportional to. It means there's other things there that we're not going to include, so don't allow them to be in the brain. All that we care about is that energy is proportional to frequency. So what does that mean? Since we already know that frequencies are related to wavelengths, we can have both of these statements be true at the same time. High frequencies, more energy. Short wavelengths, more energy. So what has more energy? Gamma rays or microwaves? What was that? Gamma rays. Okay. Why? Because it's higher frequency and shorter wavelength. Okay. Questions? Okay, let's try this one. When compared to red light, blue light is A, longer wavelength, D, higher frequency, C, lower energy, D, faster, E, none of the above. Let's vote.
Can we see this? What happened to the other thing?
No, absolutely not. Don't give it. Okay. Is it A, longer wavelength, higher frequency, lower energy, faster, or none of the above? Ready to vote? Put your fists up. Before I vote. Vote on 3, 2, 1. And mostly 2. Couple 1s. No one wanted E? No one wanted D? Okay, so maybe those come together. Maybe I should only put a couple up there. No one likes C though. Why did no one like C? Where do you like to be one of those both? It's not like an intuitive answer here. Energy, lower energy photons, what are they corresponding to? Short wavelengths or high wavelengths? Low energy photons. Low energy photons had long wavelengths. So this one's also one. There's one of these two here, longer wavelengths or higher frequencies. Or balloon light. Okay. It's higher frequency. So let's look at that picture again. Okay. Over here, shorter wavelengths on the blue side, not longer, but a higher frequency, larger numbers on the blue side. The energy of blue light is greater than the energy of red light. Now, you don't normally think of it that way. That's really how it works. In fact, you have cones in your eyes where you're receptive to different colors. How are they receptive to different colors? Well, they give different amounts of energy. Okay. Similar question. Infrared light has long wavelength and low frequency. How does UV light at a high frequency compare in wavelength? Is it shorter, the same, longer, or you cannot determine the wavelength of UV light without other information? Keep this up if you're ready. And see everyone does this one. So 3, 2, 1. Okay. All right. Almost everyone said 1. UV light has a shorter wavelength than infrared light. You're all right. Questions about this? So far, pretty boring. Let's talk about what light does. This is how we primarily get all of the information in the world through our own brains, through the purposes of light. Light does different stuff. There's 4 main properties: emission, absorption, transmission, and reflection. This is an example of the light bulbs here, this light bulb here, my laser pointer are all forms of emission. Light is coming from matter. Where there was matter, I put energy into it and light comes out. It's also, annoyingly, called radiation. Why? Because when they were first discovering these, they found out that, for example, things like radioactive materials would emit light. So the first theories of radioactivity included radiation, and unfortunately, we still have the same term for both phenomena. So you can radiate both particles and light. But we are going to use the word emission to try to avoid that, but it just means light coming from a material object. Okay? Okay. What's this one? Absorption. Give me an example of absorption. Yeah.
Darker colors.
Very good. That's a very intuitive one, right? So for example, if I'm wearing all black and I go to the beach, probably gonna have not as good a time as if I wore like a nice white dress. Nice and flowy, it would reflect the light. And I haven't said the word reflect, but it's up there. So absorption here is taking light and putting it into the matter. Emission was releasing the light, absorption is putting it in. Good? Okay, what's this one? Transmission. This is not from your car. I would argue probably 50% of you have a form of transmission on you currently. What's that? Glasses, yes. Your glasses are transmitting light, okay? They allow sunlight to pass through. Now, if you have good sunglasses, they are going to block some of the light, but you still need to be able to see, so they gotta let some of it. If you have normal glasses, like say reading glasses, or glasses to correct your vision, they should let through all of the light. You're just gonna change it slightly so your eyes can work there. Okay? That is a property called transmission. Water transmits some type of light. But it doesn't always transmit all types of light. And we'll get to that in a little while. Some stuff that is allowing light to go through. For example, this is what we call opaque. Invisible, doesn't allow light to get through. Would be not difficult for, say something like, not this laser, but let's say I were to try and click my next slide through my glasses. That's not a good example because my cover sucks. But if you have glass, radio waves don't care. They just pass through unaided. Oh, here's a better example. We're in a building. You get a phone call. The radio waves don't care that light can't get through this wall. These walls are totally opaque to radio waves. They pass through unaided, just like they would transmit through these glasses. Similarly, we take these glasses, you try to hit some gamma rays on them, maybe they go through. But for example, if you have a nice lead shirt on, or we're at the dentist, put on this lead shirt. It's because lead is particularly opaque, does not allow X-rays to transmit through the lead into your skin. Okay? So if we could see in all wavelengths, we'd be sick. The X-ray vision, it's not really X-ray vision, it's just transmission. Okay? Final one, reflection, what's that? Yeah, this is light bouncing off of something, not really changing its properties, just changing direction.
Like planets and planets.
What do you mean?
These planets probably receive it.
Yeah, so there's going to be some absorption when we talk about planets. We'll talk about color in a few seconds, but reflection just means bouncing off of an object. So for example, a mirror is a good example of reflection. Or if I do this, I can see that light bouncing off this shiny surface into my eye. And it turns out that shininess is really important in reflection. So for example, this, not very reflective, it's kind of coarse. Whereas if you use a mirror, you look very carefully at it, very, very smooth. And then you start scratching it up with steel wool or like hitting a rock against it, it becomes less shiny. Okay. Okay. Maybe this one. See if it starts. What happens to the spectrum in front of the room, that rainbow on the right-hand side, if I put a red filter into the beam? A, blue goes through, other colors disappear. B, red gets through, the other colors disappear. C, all the colors turn red. D, red stays red, but the rest turn white. Or E, it depends on which side of the grading I put the red filter. This one might be tricky. I'm trying to find out. If you're ready to vote for this stuff. Vote on 3, 2, 1. I'm getting a lot of this stuff. I've gotten about all the answers that are up here. So let's talk about this for a second. What will happen to a spectrum or red filter? So what is a red filter? So like rose-colored glasses, that's not what we're talking about. Okay. You ever heard that phrase? Anyone know what I'm talking about? The rose-colored glasses, all the red flags with red flags. What are they talking about? You put, say, for example, a red filter on, okay? Gets rid of all of the color. Only thing you see is red. Only red can pass through. So if here we have light that's white, having all of the colors hidden, and I put a red filter right here, what happens? Only red gets through, correct? And it goes through, and it comes out on this side all by itself. Okay, but if I put it right here, then white light goes in, not affected by the filter, goes through, hits the filter, and only red comes out. Okay. So red light gets through, and all the other colors. That's how filters. Okay. Here's an example of reflection. Let's talk about why reflection is so important to our eyes. In fact, this is how we see most stuff. We don't use emission very often. We're not snakes. So for example, we want to talk about something as important as color. Okay. What color are strawberries? What's that? Red. Everyone agrees that strawberries are red? What if I told you they were everything but red? Shut up, Darren, you're so annoying. Okay. Why is it red in the first place? It is absorbing white light. Okay. Green disappears. Blue disappears. Yellow disappears. And red is reflected back to our eyes. These are not emitting red. If your strawberries are emitting red, call the police. Okay? They're too hot. They do not have blue light in them. They're not emitting blue light. They're only reflecting blue light. What is this, by the way? What is this color? It's not very good. But black. This color is black. What is in this color? Is there white in here? No. How do we define the difference between white and black colors? Yeah. White reflects and black absorbs. That's very good. So the idea is here, white is reflecting all of the light. Bouncing off. What is this material, by the way? It's white. This material itself is white. And there is black, the absence of light, bouncing off of this region, as compared to this part here, where there is light, but it's white light bouncing off perfectly. Right? Okay. Is this weird yet, or is it run check? Okay. So here's the question. What color would a strawberry look if you shone a pure blue light on it? It's like a riddle you get, and you're like, I hate these riddles. Why am I getting credit for this? Okay, what color would a strawberry look like if pure blue light was shined on? Is it A, red, B, blue, C, purple, D, white, or E, black? You know, I guess. I assume no one's done this, right? No one just has like blue lights and then they look at strawberries on their free time. Anyone have any guesses here? What do you think about A? Raise your hand if you think it's red. Nobody. Nobody likes red. What about blue? Okay, a couple blue votes. What about purple? Okay, a couple purple votes. Okay. Pro purple. What about white? One, okay, 1 or 2 white votes. Black. Okay, a lot of you did not vote. A lot of you did not vote. What's going on here? We see things because light reflects off of them into our eyes where it is absorbed. Emission, reflection, absorption. Color is defined by which pieces of light, what wavelength they have, getting into our eyeball. If this emits blue, only blue light, bounces off of something that is considered red. What did I say about the strawberries? I said, are they really red, or do they only reflect red and absorb everything else? So reflection, for example, a reason something has any color at all, like black, is absorbing all light. White is reflecting all light. Blue, blue is white light's coming in, green is being absorbed, yellow is being absorbed, red is being absorbed, and blue is reflecting. That's why we call this blue. Strawberries, red is being reflected. But if your original source didn't have any red, what happens? You get any light from that object? No, and your brain will interpret it as black. The absence of light is black. Our brains don't see black. They see the absence of light. To demonstrate, okay, they don't see anything. Black, right? That make sense? Okay. Okay. Let me ask you a different question. This one sucks. We're going to unlearn a lot of things today. What color are hot things? Okay, you go to take a shower, right? And you don't speak the language, you're visiting a foreign nation, okay? You don't know what of the symbols on the knobs are. What do you use? The red one, right? You want to turn up the red so it gets nice and toasty. Okay? So all is well, right? In fact, you go home, you turn up your thermostat, you want to turn down the blue one. You want to be nice and chilly, right? Cold. But that's not what happens in a fire. Which part of the fire is the hottest? The blue part. Do we have to unlearn this? Yeah, okay. So I didn't plan showers, but apparently they're all wrong too. So you take an iron poker, a piece of metal, and you're playing with the fire because you're camping, it's fun, right? And it starts black, not emitting any light. Okay, it's also dark because you're playing with fire. Okay, and then you keep playing with the fire and it gets hot. What color does it go? Orange. And now let's say it's a really big fire. Orange, red, and then not black. Like blood red. These are still red. What's the next one? Yellow, and then white, and then blue. What? Okay. So this is what happens. As temperature increases, it goes from just emitting in the infrared. Currently, I'm emitting in the infrared. If you were to make me really, really warm, you could melt me. Let's not do that. Okay? Metals don't do that. in general. You take your iron poker, it'll get red hot poker. That's like the word. Okay? Sometimes you'll see, say, you're working with glass, glowing glass, and it's bright white. Why? Because it's really hot. Okay? And of course, right at the base where the fire is forming, where it's the very hottest, where the chemical reaction is taking place, the flame is blue. Okay? Now, why doesn't your iron poker ever become blue? What's that? No, this one's a little counterintuitive, but it has something to do with what I just said about myself. What? You could leave it for a really long time. It's going to melt first. So metal is going to melt before it becomes blue in general. Blue is very, very hot. And we'll see that in a few seconds. Okay? I know, right? That'd be cool. No, unfortunately, we're not going to see any blue lava. But good, you were drawing those connections, right? Lava is red. Why? That's hot. Okay? Really hot lava is white. There is no blue lava. Unfortunately, don't be sick. Here's humans. Okay? This is a false color. This is showing you different parts of a person's face. They're wearing sunglasses here. The sunglasses are removed from their body, which is warm. So these are quite cold. Their nose is quite cold. The cavity of their mouth is quite cold. But their skin is hot. Tie, not so cold. And this is a flame. And that flame has like a white hot flame in the middle. Okay. Cool. Okay. So now that we understand this idea of hot and cold, we're going to talk about something called a continuous spectrum. Okay. Come on. What does this mean? Hot objects, like an iron poker, emit a continuous rainbow of light. You can't see that, but that's okay. You don't have prisms in your eyes. If you had prisms in your eyes, you would always be able to see this. These are called continuous spectra, also known as thermal radiation or black body radiation. So something that's hot will put out light. And your brain is going to interpret it as either being yellow, red, blue, or white. Okay? You very, very, very rarely see green spectra. And let me show you why that is. Okay? This is a fun little law. Here's wavelength compared to intensity. Okay? The visible light right here, where we see all of our life, blue is oriented to short wavelengths, and red is oriented to long wavelengths. All of the light that, say, the sun puts out, this yellow one, peaks right in the visible. Is this a coincidence? No. Our eyes have adapted to use as much visible light as possible. This is what we have access to. But some stars are redder. They peak over here. They put out more light at redder wavelengths. So if you look at this curve right here, you could imagine I'm getting more red than blue. My brain is going to interpret that as red. If over here you look at this really hot one, you see it's putting out more blue than red. My brain interprets that as blue. Okay? So hotter objects peak at bluer wavelengths. So when we put that iron poker in, right? Started off over here, cool, not really emitting any visible light. Then it got really hot and started emitting some visible light that we could see. And as it gets hotter, the color changes. It emits more light of different colors. Okay? This has a fun law. It's called Wien's law. You can memorize this. You don't have to know where it comes from. Okay? The only thing that matters here, and the part that you'll need to understand, is the relationship between temperature and color. temperature, color. They seem unrelated. They indeed are not unrelated. Okay. Okay, so let's put this into practice. Come on now. Okay. 3 spectral curves are shown, illustrating the total energy output versus wavelength of 3 unknown objects. Which one has the highest temperature? A, B, or C? Your fist up if you're ready to vote. Okay, 3, 2, 1. Okay. Want to defend their vote? For that one. What's the relationship between color and temperature? They're inversely related. So blue things are hotter, red things are colder. So if it peaks in the direction of shorter wavelengths, then it has a higher temperature. It's kind of already makes sense if we think about it in terms of the way we talked about light. We did say that short wavelengths have more energy. Blue light has more energy than red light. Okay, so they might be related. This might be something to keep in mind. So here we have 3 of them. You might be distracted by the fact this is a tall peak and this is a short peak. You're like, oh shit, I don't know. That's okay. This can be dim, this can be dim and this can be bright. That doesn't mean that it's necessarily hotter or colder. Here you're looking for the peak. This peak is here past violet. This one is at green. And this one is at yellow. Which of those is the hottest? What's that? B. In the violet. Okay, doesn't mean it's the brightest, just that it's the hottest. You see the difference? Okay. You're going to hate this. Promise. You can use this to learn about the world. Okay. Here's the intensity versus wavelength. This stuff is going to mean something. This is going to mean something. This is going to mean something. And this is going to mean something. In fact, I'm showing you an object. If you knew how to read this, you'd be able to say, oh, that's okay. So we are going to use light as an information bearer in order to understand the cosmos. The solar system at first, later on, we'll understand the rest of the cosmos. Okay? You can determine the composition of an object, what it's made out of. You can determine the temperature. We just said how you can determine the temperature with its color, right? And interestingly enough, how fast it's moving. You can clock someone, for example, if you've been pulled over, they're like, oh, you're doing 65 and a 35. We can blame this property of light. Okay. See, I don't know if we have enough time, but we're just going to introduce this concept. There's 3 types of spectra. We've seen continuous spectra here in the middle. We will talk about this, which is called emission line spectra. This comes from something emitting light. And then this one, we understand this word already, absorption, taking that light in. So if you look carefully, there's a relationship between all of these objects. Right? Okay. In order to do that, we should understand something really briefly about atoms. Let's review a quick review of atoms. Everyone here, quantum mechanic physicists? No, okay. I'm going to assume that you don't know anything about how an atom. Is that okay? Okay. Atoms, you may have seen this sort of smaller drawing of a hydrogen. And there's a positively charged piece here and a negatively charged piece there. Oxygen kind of looks like it's orbiting, but they're saying multiple electrons in a small orbit, multiple electrons in a big orbit. And then you have this idea of combining them together. Oxygen hangs out with hydrogen. This is some bond they form, very close friends. Okay. So we talk about these as molecules, and those are atoms. Okay. It turns out that to interact with something like water or with hydrogen, they are willing to accept light. So if you wanted to go from here, this lower part, to this upper part, you need a piece of light to do it. You need energy. Okay? And similarly, if you want to make this dance form of your burrito, you need light. So it accepts energy in the form of light. And it gives off energy in the form of light. You can think of it as currency in the atomic and molecular world. Okay? But it needs exact change. So if you want to go from here to here, you can't use just any light. You need a specific amount of light. Okay? Here's carbon. The very top here, you see this beautiful rainbow. Then you see these weird little lines. Each one of those represents a jump, a step between layers in the atom that the electron wants to move up or down in. When it absorbs light, it takes one of these, let's say at this location, takes one of those pieces of light, and it moves up. And then let's say it doesn't like being up there, wants to get rid of it, gets rid of that piece of light, exactly this wavelength, and jumps down. And it turns out that every single atom has a very unique fingerprint. Not really fingerprint, but the idea of a fingerprint. I also like to think of them as barcodes. So for example, if you think about the distribution of all these lines, they're very specifically placed. You could be like, oh, I see like this color right here and these other ones here. I must know it's magnesium. Right? This one up here, it's got some red stuff, got some yellow stuff. I know it's carbon. Nitrogen has a ton of lines. Like, oh, that's so weird. This one's called neon. You might be familiar with this color before. This is not like neon green. That actually doesn't exist. Neon is an element. And look how many lines there are right over here. Anyone ever seen a neon lamp? What color are they? Like a reddish pink, right? So true neon lights, lights with neon on them, are this color. Other ones, probably LEDs. Maybe xenon, that's a fun one. It sounds like zero. Okay, here's more examples. Here's hydrogen, super boring, super simple. Got a red line over here, got this like one, okay? You look at something like hydrogen, you kind of piece it together in your head. It's gonna look a little purplish. You'd be right. Okay, so you see purple hydrogen, boom. Sodium, super boring. Okay, this is called the sodium doublet. I forget exactly what the wavelength is here, but this is what you use for a lot of like street lights. You just use sodium lights. Helium, first discovered in the sun, not discovered here on Earth. It's too light, doesn't interact with anything, it just escapes, hates being here. Almost all the helium that we create is created in nuclear reactors or nuclear explosions. So when you don't run enough of them, you start to run out of helium, and hospitals get really mad because they use them. And everyone who doesn't use them for a hospital just makes their voice sound all funny. So there's helium shortage. Neon, as we said before, over here, highly pinkish. And then mercury. This one's fun. You're going to do a spectroscopy class in lab, I think. It's fun. You get to play with lamps. They're filled with gases. You heat them up. Okay, we can use this in space. So these colors that you see here, look out into space, for example, the Crab Nebula, and we can piece this all together and say, oh, I see this oxygen over here. I see hydrogen over here, some helium, and that's telling me what the composition of this object is. Because I can just work backwards from the intensity towards the brightness. Okay. Whoops, wrong direction. Okay. An emission spectrum, we talked about the idea of emitting. This is emitting light. Just means that when you heat up a gas, maybe multiple elements in there, hydrogen, carbon dioxide, whatever you want, it's going to start glowing. And it's going to only glow in specific places. Okay? For hot, thin gases, they glow in specific colors. This is called the emission spectrum. Okay. If you instead look at it from a different direction, say this is the solar spectrum that's seen from the Earth, which is really high resolution. If you stack them side by side, it's really long, but I stacked it to make it fit on the page. Okay. This one right here, you may be noticing, hey, that's really yellow. That's sodium. Remember we talked about the fact that sodium doublet was in here? That's one of them. There's the other one. And if you look very carefully, in fact, you can find all of the elements that we've been talking about in the surface of the sun, including helium, which is found in the sun. Okay, so what do we see here? This is an absorption spectrum. There is a very hot thing, sun, and then the sun has an atmosphere, believe it or not. And above this hot cloud of gas, or sorry, above this hot source is a cloud of gas, which is cooler than the surface of the sun, and it's absorbing light. Okay, so when we have that continuous spectrum that we talked about, say for our iron poker, let's say you have an iron poker type object, and then you put a gas cloud in front of it, it's going to absorb some light, just like our filter, like our sunglasses, absorb specific types of light. It's exactly what the cloud of gas is doing, okay? And what you end up with is a continuous spectrum, see the rainbow, minus the places where it gets absorbed, which if you notice, here's this line, is the same as the emission locations. So emission is giving off from a material, absorption is taking away from the light. Okay. I know this is a lot of stuff, really hard to put all in your head. I won't be here on Thursday, but Dr. Woodney will go through the material with you for the rest of this one. We'll also do a lecture tutorial, and then we'll start talking about atmospheres. I believe the homework for this week is only on light, so only mostly on what we're covering today. Okay. If you have any questions, any comments, concerns, let me know. Slack, email, whatever. Tomorrow's office hours will also be canceled unless you want to like reschedule them personally. Okay.